Okay, welcome back again to our video lecture for Chapter 5, Section 2 from the Wiley Plus book. And the title of that section is Some Particular Forces, which is an interesting title. By particular forces, your author is going to talk about some common forces in the everyday world that particles, things, everyday things, experience. These are going to be important forces since they are common that we're going to have to be able to deal with when we analyze motion. And in fact, there are going to be three of these common or particular forces. And in physics, their names are force due to gravity, tension force, and normal force. And we'll do them one at a time. Okay? All right, so first we'll talk about what's called the force due to gravity. Let me tell you exactly what we mean by that, and then we're going to try to stick to that meaning, right? Because that's the way physics is going to be successful. The force due to gravity, here's how I'm going to label it. F subscript grav, with an arrow on top. Force is a vector, F grav. Okay? That's the force acting on a particle due to the particle's gravitational interaction with the nearest astronomical body. In almost all the situations we're going to be dealing with, not every single one, but almost all, we're going to be studying the motion of a particle on the surface or near the surface of some planet. That's what I mean by the nearest astronomical body. For us, the nearest astronomical body is Earth. And because Earth has a property called mass, it can exert what's called a gravitational force on us. Okay? And that's what I mean by the gravitational interaction. All right, so Earth exerts a gravitational force on us. F grav, force due to gravity. And if you read Chapter 5, Section 2 in the Wiley Plus book, you will find that there is a very simple formula for calculating the magnitude of the force due to gravity, or the gravitational force, or F grav. And that formula is listed right here. Notice it's for the magnitude. The magnitude of the force due to gravity acting on a particle is given by the mass of the particle times our old friend little g. So let's be clear about what everything means. The m that you see in this formula is the mass of the particle whose motion we're studying. Okay? So if I were to come over here and show a particle falling near the ground, okay, then this object, this particle, has some mass m, and there will be a force due to gravity on it because of Earth's gravitational interaction. Let's draw that force as an arrow. Force is a vector. And so we draw this force vector with its tail anchored on the particle and then pointing in the direction of the force. I think we all know which way the force due to gravity from Earth's gravitational interaction would act on a particle. It would be what we would call straight down, or in the spherical Earth approximation, towards Earth's center. And we would label that F grav with an arrow on top. Okay? Vertically downward towards Earth's center, and the magnitude of that force is given by this wonderful, simple little formula right here. The magnitude of F grav is simple to calculate. Take the mass of the particle times our old friend little g. Now I want to say a word about little g. Okay? In the physics we've studied or considered so far, little g has only appeared in two cases. Chapter 2 in what we called free fall, where we had a particle that was dropped and just let fall vertically, or was thrown vertically up, went up, slowing, stopped for a minute at a high point, an instant, and then fell vertically back down, chapter 2, free fall. Or it showed up in chapter 4, projectile motion, where the y motion had acceleration negative g, assuming plus y-axis up. Okay, so little g showed up in kinematics basically when you had free fall or projectile motion. An object is moving. That's not going to be the case anymore, that you're going to be limited to just the situation where an object's moving. Okay? There's a force due to gravity on something even if it's sitting at rest on the ground. Yes, it doesn't have to be in free fall for a force due to gravity from Earth to act on a particle. All you have to do is be near Earth. Whether you're in the air or on the ground, there's a force due to gravity from Earth. And little g is now appearing in the formula for the magnitude of that force due to gravity. So little g is no longer confined to situations like free fall. In fact, I'm going to change the name of little g. I was calling it the acceleration due to gravity, because it was always the magnitude of a particle's acceleration in free fall or projectile motion. But now what I'm going to call little g is the gravitational field strength. Wow, that's a little more impressive. The gravitational field strength of the astronomical body we're on, in our case, Earth. Okay? And so on Earth, on average, the gravitational field strength is 9.8. And I'm even going to change the units. Let me talk about that for a minute. In chapters 2 and 4, we said little g was 9.8 meters per second squared, because we were thinking of it as the magnitude of an acceleration. Perfectly legitimate. But that's not what it is now when you talk about F-grav. It's not the magnitude, necessarily, of acceleration. It's just a measure of the gravitational field strength of Earth tugging down on the thing. And in fact, gravitational field strength is gravitational force per unit mass. Force per unit mass. So now the way we're going to list the unit of g and call it gravitational field strength is, it's 9.8, it's its value, its unit is Newton per kilogram. Okay? So the value we use for g in the formula for magnitude of F-grav, m times g, we're going to use 9.8 Newton per kilogram. Now, let me mention something about that unit of Newton per kilogram. It's not inconsistent with the unit meter per second squared that we were using in chapters 2 and 4. Let me show you how I know that. Let's think about Newton's second law for, let's say, y motion. I'll remind you, that would look like this. A sub y equals F net y over m. And let's just think about units of these quantities. The unit of F net y, it's a force, must be Newton. So I'll write the symbol for the unit Newton. And m, of course, has SI unit of kilograms. So I'm just writing the unit kilogram. But a is an acceleration, so has SI unit of meter per second squared. So if I just think of units, what this is telling me is that the unit of meter per second squared is equivalent to the unit Newton divided by the unit kilogram, or force per mass in terms of units. Well, I'm just choosing to write the unit of g now as Newton per kilogram, but that's equivalent to meter per second squared. That's my point. Newton per kilogram, that combination of units is equivalent to the units meter per second squared. That has to be true from Newton's second law. Okay, so now we're going to call little g gravitational field strength, and we're going to use the value 9.8 Newton per kilogram. You will find in your book that the text uses the word weight to describe the magnitude of this force. The magnitude of the force due to gravity on a particle is its weight, W-E-I-G-H-T. And we'll use that from time to time, but please note what we mean. When we say weight of a particle, we mean the magnitude of the force due to gravity acting on it. All right, let me start to clear away some of this writing. And now let's move on down to the next comment. And I've already said this, but I want to emphasize it again. Objects do not have to be in free fall to experience the force due to gravity. They can just be sitting on the ground, yes? And Earth still pulls with its force due to gravity downward. I emphasize that again because the formula for the magnitude of F-grav includes little g, and you're used to thinking of little g when something's in free fall. But we're extending now the use of little g. Okay? So let's consider a situation, in fact. This picture I show you here is a very simple scenario, represented schematically. It's an apple sitting on a bathroom scale, sitting on a floor. Okay? You can see the apple is just drawn as a red sphere. The bathroom scale is represented by a gray rectangle, and then there's a line to represent the floor. The apple is just sitting there. It is at rest. It is not moving in any way. I am not touching it. It is just sitting on the bathroom scale. I want us to start practicing drawing what's called a free body diagram for particles. And that's actually drawn over here to the right. I'm going to write the words. Free body diagram. And that is technically everything I've just put a curved line around. Okay? That constitutes the free body diagram, let's be even more specific, for the apple. What is in a free body diagram? Well, first of all, you have to know what you're drawing the free body diagram for. That's why I wrote that, for apple. Okay, in a free body diagram for any particle, in this case the apple, you represent the particle more or less like a dot. So that red small dot there represents the apple. Then you draw, as arrows, to represent vectors, all the forces that are acting on your particle, in our case the apple. I emphasize, all the forces acting on the apple, acting on it. Not forces that it exerts on other things, only forces that are acting on it, the apple. And I contend that there are two. One of them is the first one of these common forces we've been discussing, the force due to gravity. Okay? Notice how I've drawn it. It's right here. I'll highlight it with the downward, vertically downward green arrow. That's the force due to gravity on the apple. And I've labeled it, you'll see there, F-grav. But I know that can't be all the forces acting on the apple. How could I know that? Well, I know the apple is at rest. So its velocity is 0, and its velocity isn't changing. And if its velocity isn't changing, then I know what its acceleration is. Its acceleration is 0. Newton's second law tells me that if the acceleration is 0, then the net force on the object must be 0. Because if the net force were not 0, the thing would accelerate. Okay, now I've just said there's a downward force on the apple, force due to gravity, F-grav. There's one other force, and it must exactly balance F-grav. So it must be directed exactly vertically up and have the same magnitude as F-grav. And there it is, with that green arrow that I've just highlighted. Now I'm not going to give it its shortcut name yet. I'm just going to call it the contact force on the apple due to the scale. The apple is in contact with the scale touching it, and the scale then exerts an upward force because of that. Okay? And that's a free body diagram for this apple in this situation. Two forces, one vertically down, force due to gravity, one vertically up, contact force due to the scale. There's one other part to the free body diagram. You have to also say what's your choice for your positive coordinate axis. I'm choosing a plus y axis up. That is what I call a complete complete free body diagram. We're going to be practicing more of those as we move along. But here, let me first say a couple of words of advice, some tips about force due to gravity, or its magnitude, which remember is called weight. First, do not confuse weight with mass. In everyday talk, people do that all the time, don't they? They use the words mass and weight synonymously. They mean the same thing. That's not true in physics. Let's remember what mass is. We've already mentioned that. First of all, mass is a scalar. Its SI unit is kilogram, and it's a measure of the inertia of a particle. How much does the particle resist changing its velocity? Here's a very important point about mass. The mass of a particle is the same anywhere that particle is located. If I have an apple sitting on Earth, and it has a mass, because I use a pan balance to measure that mass, it has a mass of a kilogram. If I take that apple anywhere else, I can't destroy the apple, I can't cut chunks of it away or anything, it will have the same mass, no matter where you take it. Weight, on the other hand, which we just introduced, is the magnitude of a vector quantity, right? It's the magnitude of the force due to gravity, and its SI unit is Newton, not kilogram. And there's a formula for the magnitude of, well, for weight. Weight is magnitude of F grav, m times g, the gravitational field strength. So, the particle's weight depends on what the value of g is where you are. What is the gravitational field strength at your current location? If we're on Earth, we're going to say the gravitational field strength is 9.8 Newton per kilogram. But if you go to the surface of Moon, or Venus, or way out in deep space, the value of little g is different. In fact, if you're way out in deep space where there is no astronomical body, the gravitational field strength is 0. Therefore, little g is 0. Therefore, the weight of an object out in deep space is 0. But its mass isn't 0. So watch out. Mass and weight are not interchangeable concepts. All right. Well, that's the easiest of the three common forces, the force due to gravity. Let's go on to another one. Okay? It is called the tension force. Let me try to be very clear what we mean by this, and let me also give you words of warning not to, in your own mind, change this interpretation. All right? Or start using some different meaning for tension, because it's not what physicists mean. All right. The tension force is the force a taut rope exerts on any object to which it is attached. Taut means, the word is T-A-U-T. It means there's no slack, we say in English. There's no slack in the rope. It's taut. Okay? So if you have a taut rope and you connect that rope at its ends to things, objects, that taut rope is going to exert a force on the things that are attached to it. And the force that a taut rope exerts on the things to which it is attached is called a tension force. By the way, I say rope, but physics books will also use the word string. When they also mean rope and string, they mean the same thing, right? Cord, they'll use that too. Rope, cord, or string will be common words they'll use synonymously. Let's have a physical situation to talk about tension. This simple picture shows three things. A rope that is connected at one end, tied at one end to a ceiling in a room, and tied at the other end to an object that's just going to hang from it. That object here is kind of drawn in the shape of a starburst, and let's say it just represents a piñata, like you would have at, say, a birthday party. Okay? So you've taken a rope and you've tied one end of the rope to a piñata and the other end of the rope to the ceiling in a room so that the piñata just hangs at rest on the bottom of the rope. Okay? Let's call the bottom of the rope point B and the top of the rope, which is connected to the ceiling, point T. That's what that says. That rope is taut. It's also said to be under tension. It's not slack. And therefore it exerts a tension force on the things to which it is attached. In this case, the piñata at the bottom end and the ceiling at the top end. But what I'm going to do next is I'm going to talk about a free body diagram for the piñata. Okay? Free body diagram means that you have picked an object. You're going to treat it as a particle. You've told everybody what the object is that you have picked, piñata in this case. All right? You represent the object as a particle, and you draw all the forces and label all the forces acting on the particle. Okay, so here's the free body diagram. Right there. Just encircled it. Piñata is represented as a particle. Okay, there are two forces. There's a downward force, which I'll highlight right there. That I've labeled as the force on the piñata due to Earth. But that's what we mean by the force due to gravity, all right? F grav. Vertically down, okay? There's a force due to gravity. It's the force on the piñata due to Earth. That's the downward pointing green arrow, okay? But there's an upward force because there's something touching the piñata, the rope, point B of the rope. So there's also got to be a force on the piñata due to the rope. And given that the piñata is hanging from the bottom end of this taut rope, our intuition tells us what direction this force on the piñata due to the rope is. It must be vertically up. So let me highlight that arrow now. That up arrow is the force on the piñata due to the rope, the taut rope. But that's what we mean by a tension force, right? The force that a taut rope exerts on the objects to which it is attached. So that upward force on the piñata due to the rope is what we would call the tension force on the piñata due to the rope. And to be even more careful, it's the tension at point B in the rope. So I'm going to denote that force actually with the notation I just underlined. Capital T for tension, subscript B. It's the tension at point B in the rope. I've also included my plus y axis upward. And that's my complete free body diagram for the piñata. Now I'm going to apply Newton's second law for the piñata. All right? Got to be clear what you're applying to. Now this piñata, we're assuming, is just hanging at rest. It is not moving at all. So its velocity is 0 and its velocity is constant. And since the velocity is constant, the acceleration must be 0. And Newton's second law tells me that if the acceleration equals 0, then the net force must equal 0. And if I'm applying this technically to the y direction, so what I really ought to write for Newton's second law for the y direction is that a sub y equals f net y over m. But a sub y, I know in this physical situation is equal to 0. So I conclude from Newton that f net y must equal 0 for the piñata. And that's what I'm going to actually use right there. F net y must equal 0. Well, there are only two forces. One's vertically up, one's vertically down. If the total, the vector sum of those forces must equal 0, then they have to be in opposite directions and they have to have equal magnitudes. So I can conclude right away that the magnitude of this tension force at point B, T sub B magnitude, equals the magnitude of the force due to gravity. But there's a simple formula for the magnitude of the force due to gravity. It's the mass of the object times little g. So that means the mass of the piñata times little g. And I've used the symbol m sub p for the mass of the piñata. So my point is, what am I saying? I'm saying I have learned something about the magnitude of the tension force at the bottom of the rope. It's equal to the mass of the piñata times little g, gravitational field strength. And how did I get it? By applying Newton's second law. So now let me emphasize a very important point about this force, the tension force. There is no simple mathematical formula for calculating the tension force. There's no canned formula that you can just go to calculate the tension force, like you can do for the magnitude of F grav. There's a canned formula for the magnitude of F grav. Mass times little g. You can use it any time. You need to know the magnitude of F grav. There is no simple canned formula for calculating the tension force. The only way you can calculate what the tension force is in a given situation is by applying Newton's second law. That's what I did right over here to find the tension force in the bottom of the piñata. I had to apply Newton's second law. All right, here I'm going to have you try something. I'm going to have you pause the video and try this for yourself. Now what I want you to do is draw a free body diagram for the rope. Not for the piñata, we just did that. Draw the free body diagram for the rope. Then we're going to apply Newton's second law to it, assuming the rope has a mass m sub r for rope. But for now, I just want you to pause the video and take your stab at it for yourself. We're going to have to do a lot of practice before we get good at drawing free body diagrams. So let's start. I want you to draw the free body diagram for the rope. Go ahead and pause the video. Okay, welcome back. I really hope you tried this, because this is the only way you'll be able to learn how to do this, is by practicing. I'm now going to draw my version of the free body diagram for the rope. Let me get myself some space. Okay, that should be enough room for now. All right, first, represent the object as a particle. I know you think of the rope as an extended thing, but for drawing the free body diagram, just draw a particle. There's the rope, okay? All right, now draw all the forces acting on the rope. All right, we're going to think about this carefully. Well, we said the rope has some mass, m sub r. Well, a particle with mass, here we are, and on Earth, we'll have a force due to gravity from Earth, and we know, of course, the force due to gravity is vertically down. So let me draw a downward arrow and label it. Well, I'll start with the fancy way of labeling it. F sub rope, comma, Earth. I'm being a bit fancy here for right now. That means force on rope due to Earth. It's F grav for the rope, okay? But that's not all for the forces acting on the rope, because there are two things touching the rope, yes? Things that touch tend to exert forces on other things. The rope is touched at the bottom end by the piñata and at the top end by the ceiling. So the piñata exerts a force on the rope, and the ceiling exerts a force on the rope. You have to use a little bit of your common sense / physics intuition here. Let's think about the force on the rope from the piñata at the bottom end of the rope. Which way is that force? Well, at the bottom end of the rope where the piñata is pulling, I think it's pulling down, isn't it? I think so. My intuition tells me that there's a downward force. I'm going to label it pretty big. Let me give myself a little more room here. I'm going to go ahead and slide that up. And I'm going to label that F rope, comma, piñata. That's the force on the rope due to the piñata. And the piñata is pulling down on the rope. All right, now I contend there's one more force because there's one more thing touching the rope, the ceiling. So there's a force on the rope due to the ceiling. Which way do you think that force pulls on the rope? Always keep in mind what we're drawing the free body diagram for, rope. I think the ceiling pulls up on the rope, doesn't it? In fact, it's going to be a pretty large upward force. I'll draw it up like that. And I'll label it F, rope, comma, ceiling. It's the force on the rope due to the ceiling. Even if I wasn't sure, I could use my physics knowledge to figure that out, because that rope is at rest, so its velocity is 0, and its velocity is constant, and if its velocity is constant, its acceleration is 0, and Newton teaches me that if the acceleration is 0, the net force is 0, and I had 2 forces down, so there's got to be at least 1 force up, right? So the force on the rope due to the ceiling is up. One more part to make the free body diagram complete. I'll draw it over here to the side. Which way are you choosing for your y-axis? I'm going to choose plus y vertically up. That's a complete free body diagram for the rope, okay? That's how I would want you to draw it. Now we're going to apply Newton's second law to the rope, okay? So, for y motion, a sub y equals F net y over mass of rope. I'm writing down Newton's second law for the rope. But I know a sub y is 0. The rope is not moving. So I conclude from this that F net y on the rope must equal 0. Well, in a free body diagram like this, where the forces are either vertically up or vertically down, the vector addition, the F net y, is pretty straightforward to write down. The magnitude of the one upward force must be equal to the sum of the magnitudes of the 2 downward forces. Vector addition is pretty simple when they're either vertically up or vertically down like that. So let me write that. The magnitude of the force on the rope due to the ceiling, magnitude of it, must equal the magnitude of the force on the rope due to the piñata, that's one of the downward forces, plus the magnitude of the force on the rope due to Earth. That's the other downward force. So if you have to sit and think about that for a while, that's fine. Pause the video and think about it, but it's very important that you see what I'm doing here. I used Newton's second law to conclude that the net y force must equal 0. I had a free body diagram that showed me 1 upward force and 2 downward forces, and if the net of those must be 0, then the magnitude of the 1 up force must equal the total of the magnitudes of the 2 down forces. Now I just want to interpret what these 3 magnitudes are, how to think about them. First, the one on the left. That is the magnitude of upward force on the rope due to the ceiling. Okay? Force on rope due to ceiling, magnitude. We're going to learn a little bit later about one more law of motion from Newton, called his third law. And it talks about forces between 2 things. The 2 things, A and B. And it basically says that if A exerts a force on B, then B must exert a force on A, and these 2 forces have equal magnitudes, but opposite directions, as we will see. So if there's a force on the rope due to the ceiling, there's also a force on the ceiling due to the rope of the same magnitude. But wait, force on ceiling due to rope. The force due to a rope is called tension. So my whole point is that this magnitude of the force on the left is the magnitude of the tension force in the rope, specifically the tension force at the top of the rope, because that's where the ceiling is, right? So I'm going to denote this capital T sub T. Tension at top of rope. Okay? And if the magnitude of the force on the rope due to the ceiling is equal to the magnitude of the tension force at the top of the rope, then how should we interpret the magnitude of the force on the rope due to the piñata? The piñata is at the bottom of the rope. That's the magnitude of the tension force at the bottom of the rope, T sub B. Okay? Now what's this last magnitude? Force on rope due to earth. That's gravitational force, isn't it? And we have a simple canned formula for that magnitude. It's the mass of the particle, in this case the mass of the rope, times gravitational field strength, little g. So in other words, let me go ahead and write it right down here. What has Newton's second law taught me? The tension force at the top of the rope equals the tension force at the bottom of the rope plus m sub r times g. I conclude then that the tension force at the top of the rope is bigger than the tension force at the bottom of the rope. Give myself some space there. Okay? Technically, that's true. The tension force at the top of the rope, T sub B, is larger than the tension force at the bottom because T sub T is equal to T sub B plus something positive. Right? So when you have this vertical rope like this tied to the ceiling at one end, something hanging at the bottom end, the tension force at the top of the rope is larger than the tension force at the bottom. That is technically true. But having said that, let me point out something that we're going to do almost all the time. Okay? Let me point out what we're going to do. We're going to neglect the mass of the rope. Let me explain why we can do that almost all the time. If you look back at what I had in the previous slide, I will remind you, I had a handy-dandy, simple little expression that I got from Newton's second law for the magnitude of the tension in the bottom of the rope. It was the mass of the piñata times g. Piñata. So what I see in this formula I've got right now is the tension at the top is equal to the tension at the bottom, which equals mass of piñata times g plus mass of rope times g. So on the right-hand side, I've got m piñata g plus m rope g. Here's the point. Almost all the time, the thing that's hanging at the bottom of the rope, in this case the piñata, has a lot more mass than the rope itself. In fact, we will almost always assume that's true. The thing at the bottom of the rope or string or cord has much more mass than the rope or string or cord itself. And if that's true, what I'm saying is that the mass of the piñata is bigger. In fact, it's not just bigger, it's much bigger. Let's use 2 greater than signs. The mass of the rope. Right? The mass of the piñata is a lot bigger than the mass of the rope. If that's true, then this term, mass of rope times g, is a lot smaller than mass of piñata times g. So drop the mrg, and then you conclude that to a very good approximation, the tension at the top and the tension at the bottom are equal. I call that the massless rope approximation. And so let me state it. In a massless rope, the tension force the rope exerts has the same magnitude at every point in the rope. That's what this says right here. T top equals T bottom. The tension force at the bottom of the rope and the tension force at the top of the rope are equal as long as the rope's mass is, to a good approximation, negligible, ignorable. And that's just as, how does it compare to the mass of the thing that's hanging at the bottom? Okay, all right. So that's the tension force. We'll practice with it. It can be a little bit slippery, But remember, the tension force in physics is the force that a taut rope exerts on whatever objects are attached to its ends. There is no canned formula for getting what the tension force is. You have to just apply Newton's second law to see what it will be in any given situation. Okay, last of the three common forces. It's called the normal force in physics. Let's be very clear what we mean by that in physics. We're not using normal here in the sense of the antonym of abnormal. All right? It's not like the normal force is normal and any other force is bizarre in some way. No, it's normal. The word normal there is used in a mathematical sense. In more advanced mathematics, the word normal means perpendicular in mathematics. So we're using the word normal in the sense of perpendicular. It's a perpendicular force, perpendicular to something. To what? To a surface. Because the normal force is the reaction when an object is resting on a surface, or in contact with, maybe I should say, a surface. Okay, so let me explain. Normal force is the reaction to two surfaces being in contact. The normal force acts on each of the surfaces and is perpendicular to the surface. Perpendicular to the surface. Let me try to explain how this happens physically. What I'm showing in this photograph is I have taken a brick and I have just set it down so that it is resting on 6 little coiled springs. Here you can see 3 of them. Here's one of the 3 that you can see in the photograph, but there are 6. And I just put them on a tabletop, and then I just put the brick and had it resting on top. And the brick is just sitting there resting. Now I think you can imagine that when you put the brick on these little coiled springs, they compress a little bit. They get compressed a little bit from the brick. And when you compress a spring, we'll learn, it tends to push back on whatever is compressing it. And the brick is pushing down, compressing the springs down, so the springs react by exerting a force up on the brick. And there are 6 of those springs, so there are 6 upward forces. And the total of all those upward forces together, we call the normal force on the brick. And we would just draw it as one upward arrow, like that. And notice then it's perpendicular to the surface top here. It's labeled in this book, normal force, F subscript N, N for normal. Okay? All right, now why am I talking about these springs and so forth? Because if I took this same brick, take away those 6 springs, and just put the brick on that tabletop that's in the photograph, just rest it directly on the tabletop, then you still have an upward normal force, even without those springs there. Because what you're doing when you rest the brick on the tabletop is you're deforming the atomic bonds of all the atoms in the tabletop that are right there underneath the brick. And those deformed atomic bonds act just like springs. And when you compress those atomic bonds, they react by exerting a force upward. Okay? So any object, like a brick, or a book, or a box, all right, or whatever it might be, or an apple, that is resting on a surface will experience what we call a normal force on the object due to the surface, and it will be perpendicular to the surface, pointing away from the surface. Okay? We will use this a lot because we're going to have a lot of situations where an object's on a surface, in contact with a surface. Now, a bit of bad news. Like the situation with the tension force, there is no simple canned mathematical formula for calculating normal force. The only way you can calculate what the normal force will be in a given situation is to apply Newton's second law. Let me show you what I mean. Let me draw for you a situation. Okay? That line represents a tabletop. And we are resting a brick, like the one in the photograph, directly on the tabletop. It's just sitting there on the tabletop. And I come along and with my hand push vertically down on it. Okay, I'm drawing it like that to represent me pushing down. So there's a force from me. I'll label it force on brick from me. And it's vertically down. I'm pushing down. And let me just tell you, let's say that I press downward. The magnitude of that force is 10 newtons. Now, let's say that the brick has a mass of 1 kilogram. Could you draw a free body diagram for the brick? And could you then find out the value of the normal force on it from the tabletop? You should be able to do that now. If you want to pause the video and try it, I highly recommend it. Otherwise, we're going to proceed and talk about how to do it. Okay, so we are asked to find the magnitude of the normal force. Let's draw a complete free body diagram. Represent the object as a particle. There's the brick. And draw all the forces acting on it. There's my downward force, right? Oh, it erased on me, pardon me. There's the brick. There's my downward force. So the force on the brick due to me. What else? Did you say there was a gravitational force, a force due to gravity? Of course there is. I'll just label it now F grav on the brick. Force on the brick due to Earth. But that can't be all, can there? Because the brick's at rest, so its acceleration is 0, so the net y force must be 0. The net y force on this diagram is not 0 right now. There must be one more force, in this case, vertically up, that's pretty big enough to balance the two that are down. And that one is from the surface, right? Because that's what's touching the brick, the surface. So that one the physicist would label normal force. We'll put that our plus y axis is up, that's my choice. Vertically up, that's what that is. And now we'll apply Newton's second law. A sub y equals F net y over the mass of the brick. But this brick is at rest, so A sub y is 0. So we conclude that F net y must equal 0. They're all vertical. One's vertically up, two's vertically down. So the vector addition says the magnitude of the normal force equals the magnitude of the force due to gravity plus the magnitude of my force. I'll just write it as F me. And I am asked to find the magnitude of the force due to gravity. Okay, that's what I'm supposed to find. Newton is telling me how to get it. This formula. Note, by the way, the magnitude of F grav would be the mass of the brick times little g. So there's the formula right there that I'm going to use to calculate the magnitude of the normal force on this brick. So the mass of the brick is 1 kilogram. The gravitational field strength is 9.8 Newton per kilogram. Look at the units. Kilograms cancel. Plus the magnitude of the force from me, which is 10 newtons. So what is this? 9.8 newtons plus 10 newtons is 19.8 newtons up. And that's the normal force on the brick in this situation. What if I took my force away? My pushing force. All right? What if I just didn't push anymore? It's just the brick sitting on the surface. What would be the magnitude of the normal force then? Well, did you argue that, well, all you got to do is go into your free body diagram, take out the force from you, take it out of Newton's second law, that's this one, take it away, you're left with mg, so it would be 9.8 newtons. The normal force has changed because I changed my applied force. You just have to apply Newton's second law to see what the normal force is in any given situation. Okay, so those are three common, very important forces in everyday situations. Force due to gravity, tension force, normal force. We'll be using those as we practice with this chapter. That's all for this video.